So the last talk of this session is Patrice, ex-Microsoftie and current Laceworker.
Okay. Yeah. Hi, everyone. Can you hear me? Yeah. Okay, great. It's really a great pleasure and an honor to be here today. And and also to see many familiar faces that I hadn't seen for quite a few years. So it's a great pleasure, and perhaps a little bit surprising, because I have known of Peter, or rather his work, for a long time, more than 20 years. But I only got to know him recently, actually about 2 years ago, when I joined Lacework. And so actually, Peter is one of the main reasons why I joined Lacework. And so I want to tell you a little bit, what is Lacework? What are we doing there? And I also want to mention there are two other lacers, Peter and I, but there are, in addition, two other lacers in the room today. Vagelis, who is there, and Lin Peng also, yep. So just curious, we are working on the same team. So let me start by telling you a little bit about Lacework. So Lacework is a cloud security startup. It's a big startup with hundreds of employees. And we're focusing on cloud security. So we want to secure the cloud workloads of our customers. And so Lacework is, our motto at Lacework is cloud security is a data problem. So we're building a platform that generate and ingest a lot of data about security signals. Historically, Lacework started by focusing on runtime monitoring and anomaly detection. So if you have a cloud workload running on VMs in the cloud, and you have, we can install an agent, which is a process that runs on these VMs and collects data about what processes are talking to what other machines, and things like that. And then we do anomaly detection to detect, for instance, potential attacks, or there's something bizarre going on. This machine has never talked to this one before. What's going on? And then more recently, over the last few years, this platform has been extended to have also a lot of information about configuration of the cloud workloads. So that means, so we ingest logs, for instance, how you set up the cloud workload from cloud providers like AWS, Azure, or Google Cloud, for instance. And so we have all this kind of data, some of it configuration, more static, and more about like how runtime, what's going on, dynamic. And we kind of, we have a very extensive view this way of these cloud workloads. And about 2 years ago, we started a new effort about cloud security. And now we can tell you a little bit more about this because it was announced publicly 2 months ago at a conference called AWS reInvent, where Lacework announced that we were doing this and that we're open for business. When Peter and I joined about 2 years ago, this is what we started basically working on. The CEO of Lacework refers to our group, which is about 20 people now, cloud security group, as a startup within a startup. We are a startup within a startup. So that's what we're doing at Lacework. And what is code security for us? It is roughly these things. So a big part of it is static code analysis. Oh, I should mention also, Peter is the engineering director for this effort. So we do several things. One is infrastructure as code. So we do static analysis of Terraform, this kind of code that basically you run, and that's how basically you configure your cloud workloads. Compute, storage, networking, etc. And so this is something actually that was started. We did an acquisition of a small startup just before like Peter and I joined, for instance. But the main new thing that we really have been working on is so-called SCA, software composition analysis. So this means that you have Git repos, we scan them, so we walk through the file system, we identify open source component, and then we cross-check with the vulnerability database, and we can tell our customers which open source component they have in their code repos that are vulnerable. And we can also do this from container images and also like disk images, images of machines and things like that. So that's, in a nutshell, software composition analysis. And we're also starting and doing some static code analysis in two flavors. One is quick, which is build less, so many languages. You don't need to know how to build, we just analyze the source code files. And we try to find bugs. So software composition analysis is about third parties, so open source component vulnerabilities, non-vulnerabilities. And static analysis is finding new bugs in the code of our customers directly. So two flavors, quick, which is basically multiple languages and build less, and some deeper analysis as well, which is more focused on security-related properties, mostly information flow style properties, like injection, SQL injection style attacks, things like that. So that's more about static analysis, and we have another flavor type of analysis, which is more dynamic, which is like this code-aware agent project. It's actually the main project that I've been working on at Lacework over the last couple of years. And let me tell you a little bit more about that. So what do I mean by code-aware agent? So Lacework had agents before that monitor, install on VMs and monitor essentially communication across VMs and storage and things like that. So we extended this agent to make them code-aware. By this I mean, so we can have some notion of what, the goal is to determine what software is executed on these machines. And so you can think of it as getting code coverage information, but we do it at the macro level, just at the package level. So a code-aware agent is an agent that detects what packages are executed. They are called active or not executed, inactive, so never executed. And the reason why we're doing that is that many of the software being installed on this VM is never executed. So if you have vulnerabilities in a piece of software that you never run, you can ignore it or at least deprioritize it. So the key to do this is to monitor all packages activity all the time in order to prove package inactivity. And the key is to do it at a very low cost. So the way we do this is that we monitor the file system on the machine that we monitor. And then a file involved in a package is open and executed, we declare the package as active. And we never see that even by default it's inactive. And periodically this data is sent to the Lacework platform. So as I mentioned before, the key to do this, the main innovation really is just doing it at a very low cost. So this is like as if we basically invented a new camera, which is so low cost that can be deployed everywhere, run 24/7 at cloud scale and in production. And we have lots of optimization to make it at low cost, low data volumes. So the way we monitor files, so for instance, if you have a process that accesses a file 1 million times per hour, it's like setting a breakpoint on a file. If you hit the breakpoint, we remove the breakpoint, and then so you only pay once, basically, per hour for this 1 million calls. So we use tricks like that to make the cost, keep the cost extremely low. And so it's always on and everywhere. There's no false negative and no false positive. We are not doing reachability analysis. We are not trying to make predictions to predict the future. We are basically telling you about the past. This is what we have used before in the last 30 days or more. And so as a customer, you can get all this information. So just to give you an idea, this is an old experiment I ran. So we announced this publicly in April at another conference called RSA in April. So this is an example of an experiment I ran a long time ago. So this is an example of a cloud workload with about 2,500 machines. And yeah, and so this cloud workload happens to have basically about 1,300 unique packages, and they are active packages. There are only 235 of them, and you can see some of them have critical vulnerabilities. Most are not vulnerable. And so they have 235 active packages, and 1,100 are inactive. Inactive means that on these 2,500 machines, these packages have never been executed even once over the last month. Well, actually, in this case, I have to say it's only 2 weeks, but okay. So this is what I mean by inactive. And of course, the main takeaway here is that, as an empirical observation, most vulnerable packages are actually inactive. So in this case, you have a 79% reduction of if you had to fix all the packages versus the inactive one only. And this, we have lots of data, what we cannot share, but about various customers. Of course, it varies. On average, our finding is like 65%, but it ranges from like 30%, actually sometimes it's 10%, to 90% inactive. So it depends. So this is an example of static, dynamic, cooperating analysis, where you have the static analysis here, it does, in this case, XCA style stuff. It gives you, here's the list of packages that you have, and here's the one at vulnerable, and then we can say at runtime, this is what you're running. And so, but this is just one example of several things that we want to build in the future. And so we are betting that, I mean, this very broad platform that we're building at Lacework, which both have configuration and code, and also runtime information, it allow us to really find a new low-hanging fruits, actually, by combining these different data sources. And our claim here is that the cloud really provides a new opportunity for program analysis. By cloud here, I mean the unprecedented amount of data and quality of data that we can collect about runtime. So, yeah. So, I don't know, yeah, how am I running on time? Fine. So, I just want to, to switch a little bit, say a few words about the may and the must, and to perhaps entertain your the other half of your brain for a few minutes. So I've been basically working or thinking a lot about must or bug finding for the last 30 years. And one fun, I don't know if it's fun, but it's only one pager, kind of a position paper that I wrote like about 20 years ago. The soundness of bugs is what matters. And I kind of wrote this at the time because some of my colleagues, especially in like circles like Popo, were talking a lot at the time about like program verification and soundness and what does that mean and do we care? And the main point of this one pager only was to take the counterpart and say, well, the soundness of bugs is really what matters. Hence, the connection, and I will make it to incorrectness, logic, etc. And so there's been work, of course, I'm coming from the model checking kind of community. We've also thought about this for quite a while. But if you're not interested in this topic, I just also wanted to mention one thing here, which is I want to share my favorite saying, perhaps, of all times, which is this quote allegedly by Victor Hugo, who obviously I've never met, but I'm not that old, which I think everybody in this room is either a researcher or has done research or is aspiring researcher, a researcher with a capital R. And for me, when I'm down, the thing that keeps me kind of going is this quote. There's one thing stronger than all the armies in the world, and that is an idea whose time has come. And that's our power, our role in life, well, on this planet as researchers. It's a noble activity because we are in the business of developing new ideas and technologies to back up these ideas. And that's a worthy goal. I think this is, I'm not 60 yet, but I can understand why you would devote your life to this endeavor. And for younger people, this is fun, and this is a noble activity. It has its ups and downs, but it is fun. So, on another thing about the may and the must, and I'll close with that. So, my own work in this topic perhaps culminated with this paper, mostly written, by the way, by my co-author Aditya Nori and Sriram Rajamani, and also with the collaboration of Saideep Detali, which is about compositional may-must program analysis. This is a paper that we published actually at Popo 14 years ago, almost to the day. And in that paper, it is less ambitious than what many of you want to do with incorrectness, logic, etc., in the sense that this is only for safety properties, this is for closed program, this is only for a class of C program called Windows device drivers. But in another area, we went further, and it was 15 years old work. So I just want to advertise quickly or tell you a little bit what's going on in that paper. So in that paper, we consider a program. You have a device driver, and you just have safety properties. You have an assertion somewhere in this 10,000 line program, and you want to know if you can hit this assertion. This assertion can be violated. And compositional here means the program is closed. You have main, and then you have this assertion, and can you reach it? So you have some program inputs that are clearly identified. The program has loops, pointers, and can make external calls, system calls. So it's still trivial, non-trivial, sorry. But it's not compositional, it's not an open program. There's no open adversary and these kind of things. There's no concurrency as well. And so this paper has many examples. So the way we do this is that we do this compositional in the sense that we decompose the original program into smaller subqueries. So we do interprocedural analysis, and we have summaries. And we have two types of summaries. May, or actually not may summaries, and must summaries. The not may summaries are there to prove correctness or the lack of reachability. And must summaries are there to prove reachability. You can go from A to B. And in this paper, we have examples of little C program like on this slide here, but others as well. We describe patterns where a may overanalysis may benefit from a sub-must analysis, and conversely. Or a must, and so a may analysis can be compositional in that sense, or must itself can be compositional, and then you can have this alternation with may and must summaries that you can leverage. And the paper presents a framework and an algorithm for doing this in a particular way. And it includes also a fairly expensive empirical evaluation and implementation details on a class of program only about device drivers. There are more than 16 device drivers in the paper, but that table only shows this. But long story short, it is, if you can take all the effort to engineering and implement all that, it does pay off. This compositional may-must analysis works better than a compositional may only, or a compositional must only, or just a broader, a may and a must, but they only basically connect to the top. And so, why am I sharing this? Well, it's because, and if you read at the very end of the paper, there is this acknowledgement section there, and you will see the name here of Tony Hoare. And so Tony, of course, a colleague of us at Microsoft, and he saw a draft of this paper and read it quite extensively. I was really surprised. It's probably the only paper, I have to say, that he has ever read that I've written. And I've read almost 100 of those. But why did he read this paper? And he was grilling us about these details, etc. And the reason why is really because this paper is very model checking style. It's about transition system reachability analysis. He wanted to have a version of that paper which has kind of more algebraic or Hoare logic. Incompleteness logic, as you call it, but not just incompleteness logic, incorrectness, right? He wanted to correct and incorrect at the same time, a may-must kind of thing. To my knowledge, I don't think he ever finished, or at least he didn't publish on that. I do not know, but I haven't seen a publication from him on this topic. But so, if you are interested in this, you are definitely in good company, and if you are interested in this area, I would invite you to have a look there, because especially the experimental section, we have data there about how often a may analysis may benefit from a must. What is the cost of computing a may versus a must summaries? How often are they reused? And so, and how many what are the lengths, the strengths? What is the cost of the theorem prover, etc. So we have data about that, and so that's kind of giving you a glimpse of the engineering. Once this posts to another phase of engineering, really implementing these things that you're envisioning right now, it gives you a glimpse of the type of things that you will have to deal a bit later. So in conclusion, Peter, congratulations for your remarkable career. After knowing you for about 2 years now, fairly well, I can understand why you have so many friends. And I can't wait to see what you build next as an engineer or as an entrepreneur or as a computer scientist. And I hope to perhaps do some of it with you. Thank you for your attention.
Super, thanks, Patrick. Questions?
So, Patrice, we all know from the papers, the Patrice of the soundness of bugs matters, and like you may and must, Dart, like lots of symbolic execution, lots of things. And then there's the Patrice who came to Lacework, and one might have guessed, well, Patrice is going to work on fuzzing or symbolic execution or something like that. Why not? Why did you work on what you worked on when you came to Lacework?
It's a good question. So some people worked on the same thing all their life. There's a Daphne workshop next door. Reston is still doing Daphne. I'm not one of those. I get bored. Fuzzing for me is a solved problem. I have said everything I need to say about fuzzing. There are three main techniques that people are reacting over. This is not an interesting topic to me as well. I'd rather have new challenges. I'm sorry. And so my life is at the same time exciting and frustrating because I'm just kind of bored. And so I try to kind of new challenges. And so I also like to, it is, I mean, when I joined Lacework, it was a kick in the butt for me, right? It actually did me some good. I can still do it and make new friends and learning new things. And so, and the short answer for fuzzing, why don't we do fuzzing? We don't have yet fuzzing at Lacework. I think it's going to be extremely hard to make money with fuzzing. Like I've experienced with like a previous experiment. So at Lacework, we're a startup. We need to sell, we want to make our customer happy, but we have to make money. And so we need to have both the balance between the tech and the business. And for fuzzing, it's too fragmented, it's too hard. We don't even know how people test in the cloud, if they test at all, because you shipped most of your testing to log analysis. And so I just don't know how to do a successful kind of business around fuzzing. But I don't miss fuzzing a bit. Actually, I don't think that much has happened since I left fuzzing two years ago. And so also there are some class of things that have moved to, at the time, like model checking, for instance. When I started doing research on model checking 30 years ago, it was a great topic. It was brand new. I would not, my son now, he's not going to do research in computer science, but I would not advise him to do research in model checking. And sorry if some of you are still doing that. And I'm encouraging and twisting young minds into doing a PhD there, but it's too all of a topic. I think we need fresh topics. Cloud, what we could do with the cloud. So I saw at Microsoft firsthand what telemetry did, right? So we had something called Watson telemetry. And so with the web, we could see how people are using Windows Office, where the crashes were. And guess what? 5 years later, the test branch of Windows was eliminated. There are three branches, dev, PM, and test. And because you have so much data, richer data from telemetry, you don't need to test that much. Cloud, it could revolutionize the way we do program analysis. And we need to we are at the forefront, I think, at Lacework with an end-to-end platform like that. And now, if we read enough, once we have the basics, the pipelines, we start to kind of do these kind of things, it's going to be extremely interesting space to be in, and we are riding there. So it could lead to very exciting work and maybe more impactful than fuzzing, for instance. Who knows?
Okay. Anyone inspired or inflamed? Okay. Well, thank Patrice again. We're back here at 4 o'clock.